So today we're going to finish up with data structures by looking at one non-tree based data structure that basically is the data structure of choice when you're a general purpose choice. So if you're just looking for a data structure, you're going to want to look for one that is supported by hashing, like hash tables, hash maps, hash sets. When it gets down to it, 99% of everything you do is probably going to be achievable using a hash table, right? So the other data structures that we've looked up to this point, they have their use cases. Especially if you need things to be in order, if you want to put them in order, if you want to maintain an ordering. Hashing or hash tables or hash-based data structures offer even better solutions for the basic operations of retrieval, putting stuff in, taking stuff out, etc. In fact, they offer the potential for amortized constant time operations. And what we mean by amortized, we'll take a look at it later on, but basically, you can, for all intents and purposes, you can consider all operations to be constant. Constant over the lifespan of the data structure itself. So here's the basic idea, or basic ideas. Elements are stored in a contiguous array. Why? Because random access is cheap and easy, right? And efficient. In other words, if I knew where the thing that I was looking for was at index 5, index 5 is just a memory offset. You can immediately jump to it and be done. You're there, right? But in general, we don't know where each element is stored, right? So what we do is what we do need to do is establish a hash function, right? A hash function that takes an object, right, and translates it into an integer, right? And in particular, that integer is going to be on the something like this, right? Where we're going to take, it could be a very, very large integer, right? That's fine. But what we want to do is we want to map that down to a small domain, okay? So what we mean by that is, I've got an example set up here that we're going to iteratively work on in Python. And I've created a person object. A person has an ID, a last name, there we go, and a first name, right? And I've got this toString function that prints out the last comma first along with their ID. And I've also got this overridden hash method in here. Everything in everything in Python is already hashable, right? In fact, there's this built-in hash function called hash, right? That you can go ahead and, here, let me go ahead and just have a string. S is equal to hello, right? And let's print out the hash of hello, then A, B, and C. Python, let's run this as a demonstration. Come on, hash, there we go. So very large numbers, sometimes negative numbers, right? But these big numbers, right? That's the hash value. That's just an integer value that's assigned to that object, right? The way that I had defined it up here is I am taking those three items, the ID, the last name, and the first name. I'm making a tuple out of that, and then I'm hashing that, right? It's just some number. Who cares? It's mapping an object to a number, to an integer. Then what we're going to do is we take that integer, that potentially large integer, and we map it down to a small subset of integers. So remember that z sub n, what's that defined as? Let me go ahead and recall that z sub m is equal to the set 0, 1, 2, ... all dots, up to m minus 1. Why does that help us? Right? The hash value, modded out, gives you the index at which to store something. Cool. Now I have quick lookup without having to know where it is. All I need to do is take the object, put it through my hash function. That gives me a number mod it out by m, right, with the size of your table. All right, m here is the size of your array or table. That's why we're calling it a table. It's an array, but it's a hash table. And all you have to do is put it through your hash function, and you know exactly where it's stored. It's stored at index 5. Jump to that location, right? And there's your object that you're looking for. Okay. Let's take a look at a small example here of a hash function. And for all intents and purposes, I'm simply going to treat everything as an integer. Okay. So suppose that our hash function here of x, h of x, is going to be defined as 7x plus 13, mod 8. Right? The mod 8 here establishes that this array is of size 8. So let me go ahead and create the array. There we go. 1, 2, 3, 4, 5, 6, 7, 8. Okay. Get rid of that last part there. There we go. Here are indices 0, 1, 2, 3, 4, 5, 6, and 7. Right? Okay. Now let's go ahead and insert some stuff. Insert the following. Suppose that we had an object that maps to 10, an object that maps to 16, 4, 13, and 86. Right? These are all the initial hash values. I need to get them into my table. So what is the hash value of 10 here? 7 times 10 plus 13 mod 8. 83 mod 8 is going to be what? 3. And so it hashes to this cell right here. And we put in 10. Or if we had an actual person object, for example, in the Python script there, we would actually store the object right there. Right? What about 16? 7 times 16 plus 13 is equal to, or mod 8 is equal to, anybody do that in their head? Preview here, 5. Right? 16. How did I know that, by the way, without, well, other than I'm looking it up right over here. How could I do that quickly in my head? Mod 8, 16. What happens when you divide by 8? This entire thing goes away, and all you have to do is pay attention to 13. 13 mod 8 becomes 5. Right? So little tricks like that. What about 4? 7 times 4 plus 13 mod 8 is 28, 30, 41, 1. Oh, sorry, I never put this in. So 16, and then 1 ends up being 4, right? There we go. H sub 13 is equal to 0. So 13 goes here. And finally, H sub 86 is equal to 7. Right? So 86. It works out pretty well until what? Let's add one more element. What if we added, say, H sub 100? Right. So 7 times 100 plus 13 mod 8. What's that going to be? Anyone? 1. Okay. So we're going to put 100 over here. Uh-oh. Guess what? It's occupied. Can two things live there at the same time if this were a regular old array? Nope. So this is known as a collision, right? Collisions. Right, there we go. Excuse me. When two elements have the same hash value, they collide. Is that 2 L's? Yep, okay, 2 L's. There we go. Or this is known as a collision. Oh, thank you. And 1S? Yeah, there we go. It doesn't spell check headers like that. There we go. All right, so what do you do? how do you resolve these collisions? Okay. I'm going to leave that as a question, and we're going to come back to that. What I want to do is I want to come over here and show you this process that I just showed you, right? But let's actually go ahead and implement it. Now, before I begin, do not do anything like this in real life, right? There's no reason for you to be implementing your own hash table, your own hash map, or anything like that in Python. Why? You already have a set. You have a hash set. It's under the hood. There's a hashing going on. You already have a dictionary. Under the hood, hashing is going on. Basically, I'm building an abstraction on top of an abstraction here, right? So don't do this in real life, right? You already have hash data structures in Python, and that's true for all languages. Why write your own? Java has hash map and hash set, and there is a hash table. C++ has its own collection of stuff, right? Any language is going to have this stuff built in already. But here's what it might look like if you had to build something like this. So I'm going to call this hash table. Right, there we go. Right. And it's going to be a class. So let's define the constructor here, init. Right? Oops, underscore, underscore. And we're going to initialize an array, right? Because we're going to hold stuff in an array. In this case, we're going to initialize a list, right? Self, and I'm going to call it an array though, right? Because I want to refer to it as an array. This is why this doesn't make sense in Python, because you don't really have arrays. You have lists, right? And let's go ahead and set in our max size here, max size. I'm going to set that equal to, say, 17. Oops, there we go. That means that initially we're going to have an array of size 17. I need to make sure that I do by iterating over it and putting stuff in range of self.maxSize. Right? Self.array.append none. Right? All I'm doing there is making sure that the list is of size 17 and stores nothing in each one of its locations. If I didn't do this, I would have an array of size 0. Right? Again, it's not really an array, it's a list. Okay? Now let's look at what an add method would look like, right? If you want to add an item to this hash set, first of all, you need to compute the index at which it belongs. Index is going to be equal to whatever the item is, you can hash it, because that's built into Python. It's built into every language, right? Java does have a default hash code method, right? Python has a default hash value, right? That's what I was showing you right here in this demonstration, that these are very large numbers. We then need to make sure that they're very small numbers by modding out by the hash table's max size. Max size, there we go. Once I've got the index, I can go ahead and say self.array of index is equal to that item, right? And then you can always come back and get that item. Let me go ahead and get self item, right? Same idea here, and instead of setting it, I'll return the item stored at that index, right? You're getting stuff, you're putting stuff in based all on this index. Again, if you were in a language where this was a real array, right, this would be super cheap and easy. Why? Because of random access. Right? As it is, this is since this is Python, it's already, you're already hashing stuff anyway. Now I'm just hashing it twice. To see what this looks like, let's go ahead and define the string array, the string method. Self. There we go. All I'm going to do is let me steal my code over here. Right? All I'm going to do is iterate over the elements in that array, printing out their index, and that it maps to whatever this item is. Right? And then I'm going to end the line and go forward. Okay. So I've got 3 people here. I've looked at their hash function. Yeah, go ahead. That's a good question. Yeah. So, what's one way of resolving the collisions? Make it bigger. You still need to resolve collisions because there could still be collisions, but Usually, but that's more of an issue of once it gets full. Once it gets full, can you put anything else into it? Nope. So make it bigger. Yes, you would need to rehash everything. We'll talk about that in a second here. So let's go ahead and actually create a table here, hash table. And again, don't do this in real life, right? T.add A, B, and C. Right? Those are the students. The students are Grace Hopper, Alan Turing, and Ernst Zermelo. Right? I don't know. Computer science history. Who are these folks? Alan Turing, Turing machines, et cetera, et cetera. Grace Hopper, Rear Admiral, pioneer in a lot of computing stuff, especially more engineering stuff, networking, stuff like that. Grace Hopper conference, right? Ernst Zermelo, he's just a mathematician. Zermelo-Fraenkel set theory. The set theory that you're familiar with, here's a set, here's its union, here's its intersection. The axioms that build those things are from Zermelo-Fraenkel set theory. Right? All right, anyway, let's go ahead and print this out, print T, right? And see what it looks like. Right? So, Ernst made it at index 2. Right? Grace made it at index 4. And Alan made it at index 15, right? I can also, retrieve these things. Who is at t.get A? Does that make any sense? Yeah, you already have A. Why the hell are you retrieving it if you already know who it is, right? So, for that reason, you can use the object itself like in a hash set. You just need to look it up and get where it is. Otherwise, usually what you have are dummy keys. You map a string to the person, or you map an integer to the person, or you map something to the object, which is what dictionaries are. What do dictionaries do? They take an integer or a string and they map it to an object. Right? So the get function in this case is not very useful because we're using the thing itself, right? But you can see that we can put stuff in really, really efficiently. Right? By the way, if I were to run this again, remember Zermelo is 2, Grace is 4. If I run this again, would you expect the exact same results? I did. Right? Ernst is now 3, Grace is now 5. Completely different. Now Grace is 0. Completely different. Grace is now 13. When I did this, I did not expect it. Right? I found out something about Python that the hash function that everything is based on is actually starts with a random seed every time you start up Python. That is not the case. I mean, most other languages don't have this built-in hash that is like global and universal for all the objects. Instead, you needed to find it in your object, in your class definition. So that was a surprise to me that it is. And I tried to, before class, set it so that it would be repeatable, and then I would talk about that later. But there was no way that you can do it unless you do it through environmental variables. Right? So it's done for security reasons, by the way, too. That you don't want this repeatable hash because you can attack scripts with it. Anyway, so we have some very identifiable problems here. For example, what if, and oh, hey, awesome, there it was. I got lucky here. Do we see Alan Turing on that last run? No, why? Because he must have collided with either Grace or, actually he collided with Grace because Zermelo made it in there. Or maybe Zermelo collided with Alan Turing here and overwrote it, right? Whatever the case is, whatever was here before got overwritten. That's a collision, right? And if we don't, like I haven't programmed for it, if we don't program for it, we're going to have problems because things are going to get overwritten in our table. So one way of doing that is through what's called linear probing. Linear probing is where, suppose, here, a little bit better. Right? Dot, 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 right? So if you've got a collision, because you're trying to put x in here, and it's already occupied with some key value k, right? And this also has some key value 1, 2, k3, dot, dot, dot. Basically, what you do with linear probing is, I can't put it there, so what I'm going to do is I'm going to go to the next one over, right? That's still not free. So go to the next one over. That's still not free. So go to the next one over. The very first time that you have an unoccupied cell, that's where you end up putting x, right? So for example, over here, when we had a collision with 1, what would we end up doing with 100 here? Well, we can't put it there. So I probe over to the next available cell. That's free. So I end up putting in 100. Right? Now, what's the problem with this? So suppose that we want to go with 108. By the way, I chose that to just be 8 more because it's going to also map to 1. Right? This is going to come over and map to 1. Oh, nope. Occupied, occupied, occupied. Okay, there we go. Finally, I can put 108 in there. What about 116? That's also going to be 1, right? And how is it going to probe over? Probe, 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 probe. Finally, you can put 116 in there. And we're full, right? So no matter how we try to resolve this stuff, we're going to run into problems. Right? So linear probing is one of them, linear probing. You simply check the next available cell and insert at the next unoccupied table cell. Right? You keep going until you find where it needs to be. Now what happens when you reach the end of the table, by the way? When you reach the end of the table, where do you go? Back to the beginning, mod m, right? In this case, we already know that the table is full. So what if I did, say, 124? What's going to end up happening? I probe here, probe, 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 probe. Go all the way back to the beginning. Probe, 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 probe. Basically, I'm stuck, right? I'm going to be in an infinite loop if I'm not careful. So I need to make sure that I'm taking care of all of those things, right? Probing is no longer possible if the array is full, right? Probing, or as the array gets fuller, the probability of a collision increases. I cannot spell that for anything. Collision. 2 L's, 1 S, right? Meaning that the complexity devolves into order n. Why order n? Because it's no better than a regular old list, right? Where do you want to put it? I can't put it here, I can't put it here, I can't put it here, I can't put it here. If you end up probing the entire list, right, then, or even just half of it, or even like 10% of it, that's still going to be order n, right? That's not what we wanted. What we wanted was amortized constant time here. So eventually you're going to reach a point where it's no longer worth it to continue probing, right? At some point, the fullness makes probing inefficient, and you need to rehash the table, right? Rehashing the table means create a new array of a larger size, right? And rehash all of the previous values into this new larger hash table. So if your original hash table was of size 17, right? Then what you can do is you can have this function that when it gets too full, go ahead and change this. Maybe it goes up to another 59 here. I'm choosing prime numbers because prime numbers allow you to evenly distribute stuff when you're using a linear hash function. You make it larger, the next prime up, or you make it twice as big, 34, right? But then you have to go through and rehash everything, okay? What would that look like, by the way? Here. I'll make it private here, rehash. So it's private by convention. Remember, there's nothing private in Python. Right? What I need to do is I need to create a new array, new table, and I will go through and make it larger. I'll say, can I do this in Python? Make it twice as big? I think I can, right? Anyway, new table, dot append, none, and then what I'll do is I will go through all of the old stuff. So what is it? I want to steal this code. For I in the old set, what I'll do is I'll figure in the new index here, which is going to be hash of self.array of I mod the new table's max size, self.max size. There we go. And I will put that into the new table. New table of index becomes my item, or that thing, right? I'm gonna, if it's not none. So item, let me get the item here. I'll get the ith item, and if item, then I'll do all this stuff. Do this, the hash of the item, mod the new size, the new table of that index gets that item. So why am I doing it that way? What if item is null, or not null? What if it's none? Can you hash none? I'm not sure. Let's find out. Can you print the hash of none? We'll find out after we've completed this. Right? That's a good question. And then finally, at the end of all of this, I'll say that self.array is equal to the new table. Right? I could have a bug in there. I'm not sure. Right? But that's what it would look like. You would have to go through all of the old stuff. You'd have to rehash it under this new hash function, put it into the larger table, and then go with it. Right? Say what? Oh, the old, so new size is equal to self.max size times 2. New size, good point. I could just go with x in self dot array. That's even better. That's more Pythonic, right? And then I don't need to do that. If it's not none, then we hash it and we place it in there. That's even better, right? That's much simpler. And then of course self dot size, max size is equal to the new size of the array, which is a new size. There. Okay. Let's find out. Let's answer that other question though. Can you hash none? Apparently you can. So, fine. But I didn't want to do that because then all my nuns would end up being in one spot. I want all of the other unoccupied cells to be none. But that raises another question. What if I have, what if I have an array, a hash table, where it's not full? Say that I have 5, 7, 8, 3, 2, and 10. Okay? Now, suppose that 0, 1, 2, 3, 4, 5, 6, 7, 8. Suppose that the hash value of 8 was 4, that it, suppose that the hash value of 3 was 4, right? But I already had 8 in there, so I had to linearly probe over here. Then suppose that we deleted 8. In other words, it now looks like this, right? How do I search how to search for 4. Or sorry, 3. Right. Well, remember that the hash value of 3 is 4. And so I jump to this location right here, and uh-oh, it's not there. Clearly it's not in the table, right? Yep, the next one. But how do I know that when I inserted it, I had to use linear probing to go over to the next cell? This is where dirty bits come in. Dirty bit. Right. So you have an additional piece of information here that is either 0 or 1. 0 means that it was never written. Never written to. 1 means that at some point, either it's occupied currently or at some point it was occupied, right? So it was written to. So 1, 0, 1, 0, 1, 1, 1, 0, 1. Right? Those, say, are the dirty bits. That means that when we come up here to this cell right here, right, and we see, oh, it's 3 is not there, but the dirty bit is 1. So we're forced to continue our linear probing over here to see that 3 was actually in the table. Right? We only stop that process if I'm searching for something that doesn't exist in there, 42. Right? Okay, it's not there, it's not there, it's not there, it's not there, but it's empty, and the dirty bit was 0. I know that I need to stop my search. It's not in the table at all. The problem with this is that eventually, over the lifetime of this function of this table, it could be sparse. It could only be, say, 10% full at any time. But all bits become dirty. If all of the bits are dirty, everything was written to at one point, what do you have to do to search? You have to start at the location and go all the way around until you get back to where you started. In other words, it's no different than linear search on a regular old array. Right? So no matter what, you're going to have to rehash at some point. Right? Otherwise, the performance goes down. Okay. So rehashing here. So at some point, performance will degrade. With more and more elements, all the cells become full or dirty, and a secondary data structure is needed, or some collision resolution strategy is needed. Right? To resolve this, you can create a larger hash table with new, and then rebuild all of the hash values, the indices, with a new hash function. Right? You have to rehash every single element in this table, which is going to end up being order n, a linear amount of work, right? Which is what we want to avoid. But this is a one-time cost or infrequent cost. Every time the table gets full or all the bits become dirty, you have to make a larger table and rehash everything. But hopefully you're not doing that very often, right? If you're not doing that very often, then what you have is very, very low, time complexity, right? It's a constant time, just putting stuff in. But as the table gets fuller and fuller and fuller, the time to search for things or to insert things starts to go up. When the performance starts to degrade like this, what you do is you have a spike in performance where you where you rehash everything, and that brings it down to nothing, right? And then eventually it fills up again, right? Let me draw this idea out, right? Where we've got time or complexity and time to search, right? So again, it starts out small. As it gets fuller, right? Not time, but size or size of table, right? It starts to get low. The performance starts to go down. When at some point it gets intolerable, right? It's no better than linear search. So you have this one brief spike in performance, in time complexity, in order to rehash everything. That brings it back down, right? and you have constant time, not constant time, but it starts getting worse and worse and worse. Ooh, wow, okay. It gave me an actual curve there. And then you pay for another spike to bring it down, right? You don't look at the worst case running time here with these spikes in complexity. Instead, what you do is you average it out. And if you average it out, what's it going to look like? Over the lifetime of the data structure, it's going to look constant. And that's why we say that it's amortized constant time, right? That over the lifespan of the data structure itself, you can consider that the average operation is going to be a constant time complexity. Right? There are these brief spikes where you have to reorient the data structure, but that's not often, right? You're willing to pay a high price for something that you don't do very often, as long as you're paying a low price for stuff that you do very, very often. Right? That's a time-space trade-off. Right? This is a basic time-space trade-off. What I mean by that is, let me define it more formally here. You generally keep track of what's called a load factor, right? It's used to determine when you should rehash. It's n divided by m, where n is the number of elements in the table, and m is the size of the array table, right? So in other words, n divided by m is the percentage that it is full, right? So it can be 0%. There's nothing in there, 0%. It's completely full. It's going to be 1. It's 50% full. It's going to be 0.5, right? So, yeah, go ahead. More generally, yes, if you have the dirty bit issue. If you don't allow deletions, then that goes away. But then it's not very useful data structure, right? But yeah, n would be the number of dirty bits, or in the actual in an implementation that allowed you to do all of those operations, right? So let me go. N is the number of elements, or dirty bits in the table. Right? Good point. For example, a common default would be 0.75, right? Once the array is 75% full, you rehash, right, to a bigger, say, double-sized new array. Right? This provides a trade-off. This gives you a trade-off, right? You can have a low. You can tolerate a low load factor, right? In other words, you are okay with wasting space to get performance, right? Why? Because if you're keeping it very low, that means that the probability of collisions is very low, right? Small table that's a large table, sorry. Large tables equals fewer collisions. Collisions equals faster operations, but more wasted space. More space, more wasted space. Right? What about smaller tables? Smaller tables or larger load factors, right? Higher load factors. That's going to be associated with more collisions. Collisions. There we go. And slower. Sorry, what? Why could I not spell collisions today? There we go. I can't spell. There, collisions. There we go. Slower performance, but less wasted space. Oh, there we go. Oh, no, nothing online. So it's a trade-off. Which one do you want, right? And you can tune it. You can even make it dynamic so that you can have your hash table change over time. Maybe in the beginning you have a small load factor, but at the end you have a larger load factor. In fact, that there's even these things called there is such a thing as a perfect hash function. So the use case here is, suppose that you have 10 items that you want to store in a hash table, right? and you're never going to delete anything, and you're never going to insert new things. What's the ideal? The ideal is that you only have an array of size 10, where everything is perfectly hashed with no collisions. You can do that. All you need to do is pre-compute a hash. What you do is you derive a hash function that gives you that property, right? Where these 10 items will have unique hash values, and you can store them all in one small table that never grows, never shrinks, nothing ever gets deleted, right? That's called a perfect hash function, a perfect hash table. The only use case, again, is if you pre-compute everything and you don't ever put anything in or take anything out, right? Because that changes the hash function. So lots of use cases for all this stuff. Time, space trade-offs. You want better performance. That means you're going to have to tolerate more memory being used. Right? Less memory being used means that you're going to have to tolerate lesser performance. Any questions on that? No. As an alternative to collision, other collision resolutions, right? S. There we go. So you can use chaining. Say what? There we go. Damn it. All right. You can also use chaining, right? Each cell is associated with another data structure. For example, a linked list, or a tree, or etc. So what I mean by that is, suppose that you have a collision here. Oops, come on. There we go. So we've got 10 is already here, right? We want to put in 20 because those collide. Instead of probing over, which we don't want to do, what we'll do is we won't store 10. Instead, we'll store a reference to another data structure. In this case, say that it's a linked list. Now, if we want to put 10 or 20 in the same cell, we can. All we have to do is append it to the end of that list. You want to put another value in there, 42, right? Okay, there's plenty of room, right? 42. You just can grow infinitely. Well, unbounded, I should say. What's the problem? Yeah, I mean, eventually, all you're dealing with is, instead of one linked list, now you're dealing with M linked lists. And the performance of a linked list is linear. All you're doing is cutting that by a constant factor here. Right? So eventually, you're going to have if you have too many collisions and it gets too full in that you've got a lot of lists hanging off of over here, then your performance simply just goes down to a linked list operation. Right? Alternatively, those cells could point to a tree instead. Right? And then you can, that's a little bit better performance, because if you were going to search a linked list, then that's going to be order n. Over here, if it's a balanced binary search tree, at least it's order n, log n, right? But again, you're just cutting it by a factor of m here. Instead of one tree, you have 17 trees, right? There are use cases for that, but again, it's not going to solve your problem, right? Of collisions and performance degradation. Right? So even though hash, in practice, if you have to pick an off-the-shelf data structure to store stuff, a hash function or a hash table, hash map, hash set, that's probably going to be your number one answer, right? That's going to be your number one go-to. But it still doesn't solve all problems, right? It's not appropriate in all use cases, and even under the hood here, it's only giving you this average time complexity of order 1. It's still going to have spikes in performance at some point because you have to rehash stuff. There's no perfect data structure. This is as close as you can get, though. Any questions? No? All right, so look. Yeah, go ahead.
So when you're trying to get something, you're trying to find the index by
you have to get the index through some hash function, right? So again, generally what you do is like dummy keys. So for example, I would create another person here, who equals person of, I don't know their first name or their last name. The key that I'm going to use is their ID, 123, right? And then I don't know what their last name is. I don't know what their first name is, but I can still look that up, right? If them equals t.get who was 123. That should be Grace Hopper. Print them. I hope that this works, otherwise I've got a bug somewhere. Oh no. I didn't rehash. Get. Oh, that's because she was she overwritten? No, there she is. 0, none, 1, 2, 3. Oh, it's because my hash is based on the entire thing. Let me change that so that the hash is only based on the ID. Right? I think, yep, there. Now we got her. Right? So if you're, again, it depends on what your hash is based on. If it's based on just a part of the object, generally what you do, like say in Python, in Java, a hash map, right? You've got a key and a value, right? The key, the hash value would be just on the key without the value. So you don't need to know anything about the value. You just need to know something about the key, right? And the key in this case is the ID, right? Okay. So looking forward here, we'll meet on Friday and introduce the next module, which is graphs, right, and graph algorithms. Did I already show you Network X? I think I did, right? Okay. So my suggestion is for not for the one due this Friday, but for the two where you're implementing a bunch of graph algorithms, use Network X. You're not gonna don't use the algorithms that are built into Network X, but use Network X graphs to represent your graphs. We'll do a really quick review of graphs and terminology on Friday. When we come back, again, there's no class on Monday, but on Wednesday when we come back, we'll continue with graphs and graph algorithms. All right. No questions? All right. Then I guess see you on Friday then.